very famous in our National Coordinated Soil Moisture Monitoring Network and great contributor. And I love working with Tyson Ochsner from Oklahoma State University. The Oklahoma Hydronet, developing a statewide integrated hydrologic monitoring system. Tyson, it's all yours.
Thank you, Stephanie. You're the best. Um, and thanks, Scott Jones, Mike, everybody has helped put on the workshop. It's just awesome to be here with you all and to talk about everything related to soil moisture. You all are doing amazing work, and I look forward to learning more from you as we go along. I want to tell the story about this picture that you see on the screen. It's not really a story about soil water. So I'm there in the photo so that you can see that, of course, the student is doing the hard work of installing a drill and drop sensor there. And my good friend Paul Weckler is supervising his work. And I'm there kind of off to the side talking to the farmer. He's the tall one, I'm the short one. and and I'm showing him on his phone, the app where he'll be able to get the data from his sensor. And this is in the very, very far southwest corner of Oklahoma and near Hollis, Oklahoma. And that's a cotton crop. And he's, of course, going to irrigate that crop or it wouldn't survive. And so we put the sensors in for him. This was I'm part of an effort called the Rural Renewal Initiative that addresses issues facing rural communities across Oklahoma and beyond. This was part of our work there, and so the students, followed up with him throughout the summer, made sure everything was working okay with him and other cooperators down there. And then, the students came back to school in the fall, and so I called him after harvest in the fall. I said, "Hey, Jeff, how did your cotton crop turn out down there?" He says, "It was a disaster." I said, "Oh no." I said, "I hope it wasn't the sensors." I thought, here I've steered this guy the wrong way. It wasn't anything to do with the sensors. He said, "Yeah, I ran out of water. My well went dry." And so he irrigates out of a shallow aquifer, and its levels fluctuate quite a bit year to year, and they don't have any information at all about how much water is in that aquifer when they start. And so here he's invested, you know, many thousands of dollars into this crop, and he can't finish it because he runs out of water. And this is not only one farmer in one place, but this happens in many places, especially where people are managing these shallow aquifers. And I just thought this should not be happening in, that's actually 2020 was that year. So it shouldn't be happening. We can do better than this. And so we started to look for opportunities to develop this vision of the Oklahoma Hydronet. And that's what I want to tell you a little bit more about today. These hydrologic extremes, the droughts and the floods are a national problem. And I put with droughts and floods wildfires because they're very often drought related events. And so these have huge impacts on people, on ecosystems, on infrastructure, and these extreme events are becoming more frequent and more severe. And it's not just nationwide. We can zoom into Oklahoma and see some of the effects. So Oklahoma has led the nation in a way we don't want to lead the nation in having the most drought relief payments through the Livestock Forage Disaster Program that Nathan was just alluding to, $1.4 billion over those 7-8 years there. We zoomed in on just a few counties in southwest Oklahoma where the picture was from. And just in those few counties, 3 years of drought costing 3,500 jobs and over $500 million in economic impact that we've mapped out. Flooding, that event in 2019, that was real clear on Mike's slides earlier, Michael's slides earlier. As you can see that 2019 flooding event, $3 billion in damage along the Arkansas River, and 5 people lost their lives. We've had mega fires with over 100,000 acres burned in 16, 17, and 18 in Oklahoma. And so with climate change, we see, the rains are coming harder. So this figure is showing kind of an increase in the number of days where you have more than 2 inches of rainfall coming on one day. So those are sort of extreme rainfall event days. So those appear to be increasing. And then this is our statewide annual temperature trend from 1895 to present. So it's real clear it's getting hotter. So a lot of folks have come together to try to address this. Sorry for my voice there. Ourselves at OSU, colleagues, Kirk is over here sporting the OU hat, and lots of other great folks across the state are coming together to try to address this issue. And our vision is to develop the Oklahoma Hydronet. You probably know about the Oklahoma Mesonet. It's this amazing gold standard for weather monitoring in the U.S. and beyond. And we want to have a parallel complementary network that is like Nathan was pointing out, the phrase total water monitoring. That's a good phrase, Nathan. And so it's a hydrologic monitoring system. We focus on three. If you think about where water can be stored in the landscape, there should be four, I guess, but three in Oklahoma. Number one is the soil water, and that's huge. Number two are the surface water reservoirs. That's not as big, but it is important. And number three is groundwater. And if I was further north, I would add a fourth one, which is to be the snowpack. That's it. Those are the places pretty much where you can store water on the landscape, and that's what we need to be monitoring. And we also are working within the Hydronet to develop new early warning systems. You know, there are no drought information systems that currently have an integrated measure of soil water, surface water, and groundwater. We're not doing that yet, but we should be. And we want to accelerate the research and development that we need to use this kind of information to more effectively manage droughts and floods. So that's the big picture. It's all three of those areas: the soil water, surface water reservoirs, and groundwater. But I'm going to, of course, for you today, drill in on the soil water piece. That's what brings us together here today. And so as a part of this, we are adding new soil water content sensors to the Oklahoma Mesonet. We have 120 site locations. Kirk has been to every one of them, I assume. I've been to most of them, but not all. And we have this whole suite of measurements there going back to 1994. We started soil moisture measurements in 1996 using Campbell Scientific 229 heat dissipation sensors. We can talk more about that later if you'd like. But that's what we have been using, and we have the chance now to add new and improved sensing technologies. And so as we were talking about this, we tried to really get clear on what exactly are we trying to accomplish when we measure soil water and we add new sensors. So number one, we want to improve our accuracy. It's not going to help us to put new sensors out unless they're more accurate than the sensors we've used previously. So that's one of our goals. We also want to increase the measurement depth. So we've been measuring down to 60 centimeters, and we want to go deeper than that because it's important for better estimating soil water storage in the profile, for estimating deep drainage, and for drought monitoring. We want to find, through these improvements, back to Kent's question, we want to decrease the long-term maintenance costs of our network. Right? We can't keep adding things to our network that make it more expensive in the long run. So we hope to have decreased maintenance costs. We have some secondary goals. We want to provide a 5-centimeter soil moisture product just because that is so important for remote sensing. And so that's kind of a key depth that we want to make sure to retain. We also want to produce a 0 to 100 centimeter soil moisture product that we can sort of test and compare against existing models and satellite soil moisture products like the SMAP L4 and others. We would like to co-locate our new sensors at the same depths and nearby our existing sensors so that we can document the relationship between those two. We'd like to try to match up with the depths that other people are monitoring to the extent that we can. And so those are some of the goals that we have. And so I'm going to come back to those at the end of my talk. I'm going to just kind of take a status, like how many of these goals are we achieving so far? So here's just fieldwork picture, some of the sensors. We put these in at 7 different sites where we've been testing and intercomparing different types of sensors that we're considering for the network. And so there's Kirk in the picture, and myself, and Chris Feebrick, Jerry Brown, and David Grimsley, I think, in the photo there, doing some installations. And here's an example. This is some of the latest data off of our sort of in-house data page. And so the data may look a little bit jerky. These are daily averages, and you can see I'm glad the legend is small because I'm not really focusing on exactly what sensors they are here, but the dots represent the neutron probe measurements, so we have a neutron probe access tube, and then like a clock face around it are all these different sensors. And so we have I will read them off for you. Campbell Scientific 655 is here. We've got a Teros 12. We have a Teros 15. I don't know if that's the right name for it, but a new sensor. I think there's one out here in the pod also. There's a TDR 310 from Maclima and a TDR 315. And then the sort of purplish line is our existing Campbell Scientific 229 sensors. So you can kind of see, we're just evaluating how well they line up to this neutron probe, which we consider to be an independent standard measurement of soil moisture. And so some of them are doing very well at this site. So we just trying to evaluate the accuracy. So we compared again at 7 sites the sensors with the neutron probes. I just have a few of the results that I'm showing here. These are statistics that are averaged across 7 locations. It's probably not a great way to do it, but that's just for the sake of sort of a quick comparison here. MAD is the mean absolute difference. RMSE, root mean squared error. Nash-Sutcliffe efficiency. And the R squared is what you get if you just at every site fit a regression line for each site. So you can see some of the different performance metrics there. And then the numbers in red over here are showing from a study. This is a network wide. So one thing I encourage you to do if you have a network in your reporting soil moisture data, like check it in the field. Like go out in the field, get soil samples or some other way where you get independent post-installation measure of the accuracy of your network. And so we have an MAD of 0.044 with our current sensors and an R squared, network-wide R squared of 0.685. That's with our 229. So we need to beat that. And the good news is that some of these candidate sensors look like they can beat those metrics. Not by a lot, not by as much as you might hope, but it's not that easy to come up with a sensor that works across all the great diversities of soils that exist out there across a whole entire state. But you can see some of these do appear to offer better accuracy, so that's good. And just recognize that, the sensor that gives you the best correlation at one single site may not be the most accurate sensor across a whole collection of sites. So just keep those differences in mind. Okay, now how are we going to install below 60 centimeters? So Kirk has clearly told me from the beginning he doesn't want to dig a whole bunch of pits. Actually, I don't want to dig a whole bunch of pits. So we're looking at these, borehole kind of approaches where we can get sensors down to 100 centimeters or more without a backhoe or without an army of graduate students. And we really just don't want to disturb our sites that much because guess what? Some sensors are going to fail and we're going to have to dig them up again and do it again. So we're really looking at these borehole methods and a couple different approaches to that. There's a Teros 12 kind of approach where you can, make a borehole and then with a special tool here, push the sensor into the side so that it's in maybe undisturbed or at least less disturbed soil to the side. So that has some, benefits to that, and there's also some trade-offs to that as well. Another approach is where you can just go put a borehole down and then push the sensor straight into the bottom of the borehole. Okay, so that, again, there's some trade-offs involved here in these different installation methods, and we're trying to understand those trade-offs and what might work best for us. As we do all of this, we're really seeking to make evidence-based decisions. What gives us the best data? I really don't want to hear, I don't want to say, if somebody asks me, why did you do that? I don't want to answer with, well, that's what these other people did. I want to have some evidence why we're doing it. Okay. Reduce long-term cost. Well, the long-term cost, as Ken has mentioned with us earlier, may be larger than the initial cost, right? Maintaining is more expensive than installing. They're hard to estimate the long-term cost. Here's at least 4 factors that go into it that you maybe have thought about, maybe didn't. Are you going to have to do sensor-specific calibrations for each sensor as it comes in? How many sensor failures are you going to have? How much time and effort is going to be involved in QC of the data? How many site visits are going to be required? These are all factors. I can't estimate all of those. I did come up with some estimates of failure rates based on existing networks. And please, let me just say these are very, very crude and preliminary estimates. So just take these as an example of the kind of estimates that we would need. For our 229s and Oklahoma Mesonet, we're estimating almost 8% per year of those fail and have to be replaced. Now, we do have some that have been in the ground since 1996 and they still work. Okay, so just you got to understand the nuances there. But on average, about an 8% failure rate. There's a nice job by Tim Wilson and others in 2020. They actually published a little stat in their paper, the failure rates for their hydroprobes in the U.S. Climate Reference Network. It was about 16% over 3 years. That comes out to just over 5% per year failure rate on those. This last one, I'm really kind of winging it here, but kind of piecing some things together. It looks like the Acclimas that have gone in on the CRN network maybe have around a 4% per year failure rate, but all this is sort of very preliminary. But all that comes into the cost of maintaining these things, because every failure is going to be a site visit. All right, now optimal sensing depths. Okay, how many? What is the scientific basis for the current sensing depths? If we're going to do 5, 10, 20, 50, and 100, why are we doing those? And I think Nathan's comment earlier was excellent. One reason why those depths are being used is those are long ago recommended depths for measuring soil temperature, and they've persisted. Okay, another question we should ask is, what combination of depths give us the best estimate of soil water storage? 0 to 100 or whatever, 0 to whatever your bottom is. And so how many depths are we going to need to measure to do that? And then, how important is it for us to use the same depths across networks? Is that important? It'd be kind of nice if we could all agree on a set of depths, but it's hard to know how much importance to assign to that. So here's a little picture, because I'm a visual thinker, okay? And so follow with me on this picture if you would. This first one here, this is what we currently do in the Oklahoma Mesonet. 5, 25, and 60. So the thicker black line represents the depth of a sensor, and the colored shaded region represents the soil layer that it represents. Okay? So the 5 represents the 0 to 10, and the 25 represents the 10 to 40. Does that make sense? Okay, so this is what we do currently, and we're saying we want to extend this deeper. Here's what some other networks do. There's a 5 centimeter that represents sort of 0 to 7.5, and there's a 10 that represents sort of 7.5 to 12.5, and then just on down, you can follow it down. I can't name all those depths, but you can see the picture. Here's 3 options we've thought about. We could do 5, 25, 60, and 100. That would give us these layers. Or we could do 5, and I just can't do 10 in good conscience. We could do 5 and 20 and 50 and 100. That'd be like this. Or what if we got radical and just thought, we should really just have incrementally larger layers going with each sensor, and that would give us 5, 20, 45, and 80, actually. So like what actually works best? Let's make the decision based on that. Well, so we don't know yet, but here's some data, because I like data, and I bet you do too. So if these are errors in estimating the 0 to 1 meter, 0 to 100 centimeters soil water storage. Okay, so the first one is what we have here, the Oklahoma Mesonet. Well, we're not going to do a great job because our deepest sensor is only to 60 centimeters. Okay, so you can see we often overestimate. We have a positive error there. So our errors are, kind of large. We're not recommending that. That's just kind of there for reference. If that was with 3 sensors, if we use 5 sensors at these depths, 5, 10, 20, 50, and 100, we would do a little bit better. Or we would do better with that. So that seems good. But we could actually do better still with just 4 sensors at 5, 25, 60, and 100. And here's a couple others we could do. 5, 20, 50, and 100 is not too bad. And that sort of radical version of 5, 20, 45, and 80 is maybe better still. So we're trying to get a hold of data sets with these detailed resolution, soil moisture profiles, and see what sensor depths actually make sense and try to make an evidence-based decision. And it's a little bit embarrassing to me that I'm so ignorant and I don't know. So I'm trying to figure out some real basic stuff here. Okay. All right. So let's check back to our goals. This is almost to the end now. So can we improve the accuracy of our relative to our existing sensors? It's that color blue. I thought, well, it's not yellow and it's not green, like, traffic signal. So yeah, I thought blue. Yeah. Yellow and blue makes green. So so it's blue. We're sort of probably we can do that. Can we go deeper than 60? Yeah, definitely we can do that. Can we decrease long-term maintenance cost? I'm hopeful. I think we can. I'm not 100% sure. Can we do 5 centimeters? Yeah, we can do that. Can we do 0 to 100? Yes, we can. The problem is these last 2 goals are in conflict with each other. So we can choose to either co-locate with our existing sensors, or we can choose to either match what other people do, but we can't do both. So that's those 2 are a little bit in conflict with each other. So that's it. Appreciate your time and attention, and thanks for the opportunity.
Questions for Tyson? Oh boy. Starting over here.
Great talk, thanks. So I've heard it a little bit, a couple times today in a roundabout way, but how important, or maybe I haven't heard it, but it's been alluded to, how important are the actual soil properties for the decision making of the depth of the sensors? And along that line, just recognizing the difference in the purpose of the end goal. So the soil properties conversation.
Yeah, thank you for that. They're really important. And the most important one is, how deep is your soil? That's hands down the most important soil property is how deep is your soil. And because if you don't know how deep it is, you don't know, what's your rooting zone that you're working with. And then you don't really know how many sensors you're going to need or how many you can fit. So what I struggle with, because if we're ready to deploy network wide to put in 100 centimeter depth, well, we might only get to 100 centimeters at half of our sites. And so would I have been better off in hindsight to put them at 80? So soil depth is the most important soil property in this context. Now, other soil properties like layer horizons and so forth, those are also interesting and relevant, and we want to sample the soil and characterize it. So when we go out, we always take soil samples to characterize those properties. But in terms of trying to do a full profile description and match sensors to horizons, I wouldn't recommend it unless you're doing a study on soil genesis and morphology, and then I would.
I'm curious what you think the water table and the water table fluctuation has to do with that depth that you go to. So what about that zone between your lowest soil moisture sensor and the highest water table height?
That's a great question. And it's super site specific, right? In terms of what your water table depth is going to do, and if it's ever going to be near the surface or if it's never going to be there. And so it's really site specific. I think all the kind of thinking and everything that I showed up here is really geared around the thinking about plant, water uptake and soil water uptake. But it's not really geared around thinking about shallow groundwater interactions with soil moisture. And if that's your environment, I might think differently about that. It's really a great question. Yeah.
Switching to the other side.
So, playing devil's advocate on the 10 centimeter, you knew you were going to catch that, right? What if you put one in, even just for the temperature? Would that change your calculus on, I know you were looking at the errors for different configurations and different numbers of sensors. What if you just put one in just to pick up the temperature and saw how that, I mean, what's your intuition about how it would impact the calculus on the rest of that then? Mike's asleep at the wheel.
Courteous for the onliners. Here we go.
Okay. Yeah, it's great. I think that's why the 10 centimeter depth is often there. It's because it's a traditional soil temperature measurement depth. And you could certainly put a sensor there for that reason. It's just a costly thing to do if you're going to support it network wide. And I don't think the cost is worth it. I started my career in soil temperature. I love soil temperature. I'm a soil temperature guy. You tell me the daily average temperature at 5 centimeters, I think I can tell you the daily average temperature at 10 centimeters also pretty well. So it's like not really worth, not the cost benefit really isn't there for me.
Last year was my first year attending this conference, and so I'm listening to everything people are saying. And I think I remember some discussion about the 10 centimeter being, I get now that you're trying to reduce the long-term maintenance, but it potentially could help as a redundant measurement for the 5 centimeter. If one goes out, then you still have that other to rely on and infer on. So that's what I have in my head on that. Yeah. So good or bad, I don't know. Actually, my real question kind of developed listening to other people. So on your chart, you were noting the point in which a sensor was, and then the representative depth, which that, yeah. So I'm curious if extrapolating that point measurement to a depth could really be related to the horizonation and the soil profile instead of the standard. If that would be, if you could go site by site and do that especially when you're calculating plant available water for 0 to 100.
Yeah, I appreciate the question. That really brings up this gentleman's question about the soil properties, because they are always important, and yes, they could probably be used to more thoughtfully interpolate or integrate the soil water profile. If I was the sand content, if you could just know the sand content every, I don't know, 5 centimeters down through your soil profile, you would know a lot about how to interpolate those between measurement depths. That would go a long ways towards addressing that. Yeah.
Hey, thank you for that presentation, Tyson. I was thinking back to your first photo there. Can you speak to a little bit to how you've engaged stakeholders on this and how you've brought them into the network and not advertised, but you got it out there that you'd like to do some more monitoring across the state of Oklahoma?
Yeah, thanks. We haven't done nearly as much of that as we need to. So the the stakeholders right now are mainly engaged two ways. Number one, through all those different agencies that I listed that are participating, they all, put us in touch with their stakeholders and pass along the concerns and interests of their stakeholders sort of secondhand like that. But since we're at the very early stages, we don't have anything really to show yet to our stakeholders. So we haven't had any, stakeholder meetings or anything like that. But we need to and intend to. So part of this is about extension. Extension is something that I don't know if we've really touched on here in today's meeting, but within a land grant university system, extension is really important. Extension will play a bigger role for us in this Oklahoma Hydronet moving forward in terms of developing products that meet specific needs of particular stakeholders. And so we're sort of at the early stages of that.
Okay, folks, with that, we're going to wrap up. Just catch Tyson afterwards for questions if you had some more. We're going to wrap up our afternoon session. Thank you to all the presenters and hanging in with our afternoon. We do want to have checked to make sure that we didn't miss any presenters because we did have some absences